Hello and welcome to this screencast on colinearity in linear models when we have multiple predictors. As we discussed in class, that when you are looking at essentially multiple regression or a linear model with multiple predictors, not only do you see adjustments of the coefficients in your estimates in partial order squareds, but if there is a great deal of correlation among the predictors, if they're highly correlated to each other, or if in a model where you have categorical predictors, there is a strongly unbalanced design, then you can actually run into some problems. Essentially, you will get colinearity among your predictors, and that will influence your estimates and will increase standard errors as discussed in class. And you can get problems of, like I called in class, the bouncing betas, where your estimates can really bounce around, your standard errors get inflated, and it can make interpreting your model very difficult, and you need to potentially consider what to do. So let's take a quick look. We're using the same data set as we did before, so please load in the data frame from before. It's at the top of the script of the multiple regression colinearity script. And let's just take a quick look at a couple of plots. So here's an example of plotting the tibia length versus femur length. As you can clearly see, these two predictors are quite positively correlated. We can perhaps get a better look of this if we use one of the lattice functions called XY plot, where we're going to look at the relationship of our response to the three predictors. And it's hard to see from this one. It's clear that it's hard to see what the relationship is between sex cone teeth and the other ones, but you can clearly see there's a relationship among those predictors. And there's one other XY plot that we use the same function for, really just to look at femur and tibia and tarsus. And again, you can see that strong positive correlation among all the variables. We can also express this using correlation, so I'm just going to make a small matrix with just those three predictors, femur, tibia, and tarsus, so it's just those three columns. And we'll look at the correlation among those three. We're just going to use cases where we have complete information for the pairwise correlations. And what we see is that the correlation, say, between tibia and femur is about 0.7, femur and tarsus somewhat lower at 0.57, and then tibia and tarsus a little bit lower than that, about 0.5. We might ask the question when we see examples of this, especially when we're looking at morphological traits. A lot of people say, well, you perhaps want to look at log transformed variables. But as you will see here, that doesn't actually change the difference if we use log or non-log transformed data. And so we won't worry about the log transformation here. So we can run the full analysis, again, looking at sex cone teeth as a function of femur, tibia, and tarsus length. And of course we get our summary from this. And if we get our summary, what do we see? Well, one thing we see is that the femur seems to be explaining essentially nothing. Now I won't show you now, but if you just run sex cone teeth as a function of femur, chances are, I can't remember for sure actually right now, but chances are you will see a significant result and a somewhat different estimate. So what's going on? We can look at this again in the context of ANOVA, but it's essentially giving us the same information here. Femur seems to, be quote-unquote not important relative to tibia and tarsus. Well, what might be going on? So if you remember from the lecture on colinearity, we talked about two ways of examining it quantitatively in addition to actually looking at, say, those plots and the correlation matrices we did just a moment ago. We can use the condition number. And it doesn't really matter how we're calculating it now, but essentially, just remind yourself we're using the design matrix. So this doesn't depend on the response variable, only on the predictor variables. And essentially, we're going to create a new matrix where we're multiplying the transpose of the design matrix by itself to get a square matrix. And then we're going to extract eigenvalues. And essentially, we're looking at the ratio, the square root of the ratio of the largest to the smallest. And if the bigger it gets, the worse the problem we have. And our rule of thumb was approximately 30. So I've written a little function that you can just use and copy out for your own work, just called condition number. And so if we call condition number, number for our full model, we see we get a very large condition number, three times greater than 30, so quite large. Clearly we have some problems here. Now I also mentioned to you that we could use the Vif function. And here is the Vif function that you can use. There's actually in the car library. So if you haven't already installed and called the library, please do so. It's already available in mine. And you can do it just by going VIF lm full, and it'll give you the variance inflation factor for each of the terms. And like I mentioned, VIF, some people have this rule of thumb of 6 or 10 as being when you should be concerned. But if you remember, it's essentially a scale to your standard error. So when we see the VIF for femur being 2.3, it's essentially saying that with these other predictors in the model, with the colinearity, your standard error for the coefficient associated with femur is twice what it would be otherwise. I won't go through it here, but if you want to figure out how to do VIF by yourself, by computing the tolerances and then just the inverses for those, this is just showing you how to do that. And you will see, I'll just show you with the VIF tarsus that we get 1.51. Whoops, I lost that, 1.51. Sorry, let's go back to here. And that's 1.515, which is about what we see here for the tarsus here, 1.512. So you'll get approximately the same answers with these. So like I mentioned before, and I think this is important, at least in terms of the rule of thumbs of VIF, VIF tends to underestimate the degree of colinearity. Condition number is perhaps better for the overall model. VIF is good to use to get a sense how each individual variable is being influenced. We can also look more fully directly at the correlations between the parameter estimates itself using the Vif function. So we're going to create a matrix called cov_par_mat. And if we look at it, this is giving us the covariances for parameter estimates. So if you remember that if you want the standard errors from these, you can, on the diagonal, each of these could be, you take the square root of each of these, and it'll give you the standard error associated with those coefficients. Those would be the same numbers. On the off diagonals, this is giving us the degree of covariation among those parameter estimates. Again, not for the observations, but in the parameter estimates. And we can actually, this just does this sort of in a more complicated fashion. This will give you the actual correlation among it. There's actually a useful function that you've seen me use before called cov_to_cor. And if we just take this cov_par_mat, put it in here, it'll actually give us essentially the correlation matrix among parameter estimates. So we can see that in some cases it's not so bad. Say femur and tarsus, there's a negative correlation, which we expect. Negative 0.35. It's not tiny, but it's not huge. Femur and tibia is much larger, which is to be expected. They tended to be much more strongly correlated. So there's some issues definitely here. Okay, so these are ways of diagnosing it, looking at these sort of three different things. Well, so before you fit the model, you can look at the pairwise plots among predictors, or you can actually just look at the correlations among predictors. Once you fit the model, you can use the design matrix. And again, remember that none of these depend on the response. The design matrix does not have the response variable in it, but you can use the condition number, you can use the variance inflation factor, and you can also look at the covariances or correlations among parameter estimates. Now let's spend the rest of this time looking at the same problem, but instead of doing it for continuous predictor variables, let's just look for a case where we have some unbalanced designs for the same data. We're going to look at two categorical predictors, genotype and temperature. Both of them have 2 levels each. You've seen them before. We'll just fit this model. Let's call it model.x. Now before we actually look at anything, I'm going to just use the tapply function here to make a little table to look at sample sizes for each of the groups. So reared at 25 degrees, individuals for the DLL genotype, we have 412 of them. For that same temperature, for the wild type condition, we have almost 600 individuals. So you can see a fair bit of lack of balance there. We don't need to look at the head of the model matrix right now. But we can do the same thing and ask about variance inflation factor for this model. So what we actually see is that genotype and temperature, it's essentially the very little evidence of variance inflation factor, because we're essentially multiplying our standard errors by 1.003 in each of these cases. So the lack of balance in this particular case is not causing much problem. If we had much smaller sample sizes and sort of similar degrees of lack of balance, we would actually have a much worse problem. But because the sample sizes are large, it's not becoming terrible. But like I mentioned in class, often my experience with unbalanced designs and colinearity is there's a big cliff, and it's hard to predict where that is, after which the lack of balance can really mess things up, and you'll go from having very small variance inflation factors or condition numbers to very large ones. How big is the condition number? Well, we can use the same function we just wrote above, and we see it's about 3 and a bit. Well, so that's pretty tiny, so we're not worried. Well, let's start adding some complexity to this model since we wanted a much more complex model. Let's, in addition to the additive genotype and temperature terms, let's look at the interaction among those terms. We're not interested in the model coefficients or anything right now, just in how much colinearity. In other words, in this case, how much the lack of balance is going to sort of mess up our parameter estimates, or at least the standard errors for those parameter estimates. So for the VIF, for the model with interaction, we see that it's certainly much larger. It was about 1 before, now it's almost 2 in each of these cases, 3 for the interaction term. So clearly we have more of a problem. How big a problem? Well, again, condition number is sort of our overall estimate of the degree of colinearity. It's still pretty small. It's certainly well below our rule of thumb of 30. I wouldn't be too worried in this particular case. Of course, this as well is not the degree of model complexity that we would need. So we'll add one additional level of complexity to see what starts happening. Here we're going to add an additional term, line, that's also a factor, which has 26 levels in it. We're not going to worry about additional interactions between line and other variables, although we would want to model those for addressing questions with the data. And again, we're not interested so much in what this model has to say as what this additional model complexity does to our degree of colinearity. Again, specifically due to the lack of balance in the design. And what we see here now is first this condition number, it's now shot up to 34. So it's the degree of colinearity seems to be much more of a problem here with this model. We can also look at the VIFs, and it provides two different versions of the VIFs, essentially one which adjusts for the number of treatment levels or degrees of freedom. So these are the ones, the GVIF are really the ones you're interested in when you have multiple factors with, and some of those factors having, say, more than 2 levels. And here again, the VIFs seem to be suggesting there's not much of a problem, despite the fact that condition number is perhaps suggesting there is more. And this is, again, one of those things you wanted to deal with. How do we deal with this? Well, this is a lack of balance in design, so if we want to model these interactions, we may be stuck with it and having to just say we recognize there's this degree of colinearity, and it messes up our estimates. And just for your information, this actual model is still simpler than we would actually like to fit, but we'll use a mixed model approach later on in the course to examine this more closely. Well, thank you, and this ends this screencast.